All right. Thank you, everyone, for joining this webinar. My name is Jensen Chen. I would like to thank you for joining our Dynaform webinar, Blank and Trimline Developments for Near Net Shape Simulations to accurately predict blank outline and trimline in highly efficient way. Today, I'm hosting this webinar along with my co-hosts, Ming Zhang, and colleagues, Curtis and JT. Here's a YouTube channel for those who missed our previous webinars related to Dynaform. Please go to visit our YouTube channel, ETA Info 1 at YouTube. You may check some of the Dynaform webinars as well as other videos regarding our other products. Blank and Trimline developments is one of the features in Dynaform version 6.1. Today, Ming will cover two main capabilities in BTD. One is local blank development, and the second one is local trimline development. Okay, just a quick overview about ETA. We are an advanced engineering solution provider serving the automotive industry since 1983. We are also developer of engineering software such as Dynaform, Precis, and VPG Suite. We have been developing Dynaform for the past almost 4 decades. It's starting as a small metaforming code for Ford Motor, and eventually, we release commercial versions. And the version 6.1 was released last year. We are going to release version 6.2 in just a few more months. The market spectrum of Dynaform ranges from aerospace, automobile and motorcycle to electrical and electronics industries. Basically, any industry that involves sheet metal stamping is potential Dynaform target. Currently, Dynaform consists of 6 distinctive modules. Blank size engineering, BSE, is used to quickly perform blank material cost estimation, as well as improving blank material utilization rate. Formability simulation, FS, is aimed for deep drawing, progressive and line die stamping simulation. It helps to improve tool making cycle time by solving stamping defects prior to constructing the actual tools. The die evaluation, or DEval, is utilized to quickly evaluate draw die design, trimline, and scrap sizes. For die structure, scrap flow, and sheet metal transfer, the die system analysis can be employed to investigate various die system related problems, such as die structure fatigue, scrap blockage, and interference during sheet metal transfer process. Dynaform also consists of blank and trimline developments, which is utilized to conduct near net shape simulations for prediction of blank outline and trimline using an iterative optimization approach. Lastly, the tube bending and formability module is utilized to conduct CNC tube bending and tubular hydroforming simulation. With all the modules, Dynaform helps to quickly resolve complicated sheet metal stamping issues. Today, Ming will conduct a couple of live demos on BTD. The first case is about local blank development of blank outline holes. This example illustrates the ease of setting up BTD. The second case is about local trimline development of multi-stage operation. BTD will optimize trimline within a few iterations. After the live demo, we will proceed to Q&A session. You may type in your questions in the chat box. Now, I will pass the torch over to Ming. Ming, over to you.
Thank you very much, CC. First, let me share my screen. All right, welcome everyone. My name is Ming Zhang. I am the support lead of Dynaform in North America. Today, I will demonstrate 2 examples. The first one, we'll be looking at the blank outline development. If you have any question during the demo, you can type them in the QA box, at the bottom from Zoom. Also, we will have a live QA section after the demo. On my screen, this is multi-stage simulation. The blank is defined by outline here. And also, if you look at the operations, we do have 3 stages for this simulation. The OP10, we will have a forming. It will form the center area and also a little bit on the, let me first play the animation, hide the OP30, or show the operation 10 only. So this is the first stage. Yeah, let me play the animation. So you can see this upper and lower two, and also this binder will form the center area and also a little bit on the side. And then if I move to the second flanging stage, it will, form a little bit more than 1 sec on the OP20. So it will form the side area. So the pad will hold the blank from the top, and then the punch will goes down to form the side flanging area. And then for the OP30, okay, it restrict the side area, so it form, the flanging area a little bit more downward. Okay, so if I look at my blank from initially, let me hide the tools and show the blank only. This is the initial shape of the blank. Will be optimized this blank based on our target line, and it is the final product profile line. We are not going to focusing on the inner these cutout, so because we can trim this cutout later. So we will be focusing on the outline and also these two holes, because the reason is after we flange it, these holes will be vertical. So for defining this multi-stage simulation, you can refer to our previous webinar for the FS module forming simulation module. So after we finish the setup of these three-stage simulation, we can see there is one tab is called the Trimline development. Once we go here, we can simply add our blank outline. So in the database, I can simply pick up the blank outline here and confirm, and then go ahead and pick up my target line. This is the product outline. We also import it into our database to confirm. And also, we are able to select the region we want to optimize. It means we don't have to optimize the whole line. If we only want to run the optimization for this flanging area, maybe start from here to here, we can also do that. Check the local region option, and then keep going to run the optimization. In this case, we are going to do the optimization for the whole outline. And also we need to add these two holes here. So I just add another group for optimization and pick up the hole from left, and then pick up the target from our target line group. Yeah, similarly, I will add another group for the holes on the other side. Yeah, actually, this target line is in the middle of our blank. So it depends on what the geometry you use. If it's different, you can just increase the tolerance for the optimization. Make sure the result is converged. Okay. So now I just finished the defining of our blank outline and the holes, and also our target lines. Also, some parameters here under this tab, I want to make a quick introduction. First is that this target stage. So for multi-stage simulation, we don't have to define the target at the last stage. We can use OP20 or OP10 as our target stage. In this case, our target stage will be the last one, so it will be OP30. And also, we do have some parameters here, the number of iterations and the tolerance. The tolerance is very straightforward, means the software will compare the final result, compare the edge on the final blank with our target line. If the difference is smaller than this tolerance, the software will consider it as converged, then the iteration will stop. If not, the software will calculate the compensation and modify the blank outline or trim line again, and rerun the simulation run another iteration from beginning, and then check the result again. So here's the number of iterations. Means if the simulation is not converged, even after 5 iterations, the software will stop, no matter it's a converge or not. On the right, we do have this restart from iterations. Means if you only finish 2 of the iterations, but you want to check the result, you just stop it. But you want to restart from iteration 2, then you can restart from certain iterations. And also, we do have this blank mesh size. Means after each iteration, after the software modify the trim line or blank outline, what size you want to use to remesh the blank. Okay, so for saving our time, I already have run this simulation. A simulation like this will will take about less than 2 hours to finish. Also depends on the element size and the number of elements. But if some designer manually modify the streamline, it's easily go back and forth, modify the line and rerun the simulation, and then go back modify again. It may cost 2-3 days. So this will save a lot of time. So once the simulation is finished, I can go here and select the view of my result. First, I will go to my history. So by checking the history, the software will bring all the iterations to the software. You will see it just in a few seconds. It is loading all the iterations from the optimization. Okay. Now by default on my screen, it is showing the last iteration because it got converged. Once the optimization finished, you will see a small window pop out that says, the tolerance is smaller than 1 millimeter, and the simulation, the optimization is converged, and the simulation they will stop. Okay. If I turn off it, just turn on the first one. Okay, now you can see by using our initial blank outline, this is the part edge. And also you can see the deviations we plot on the target line. You can see read the difference. It's quite different from the center area, and also there are a lot of deviation here. Okay, so after the first optimization, actually it's the baseline run. The software do the compensation calculation and modify the line and start the next one. So this OPT1, which I'm showing on the screen, this is the first optimization by using the optimized blank outline. So you can see it has improved a lot, but still in some local area, it's not perfect. And then it will keep running until it reaches the target line. Means this tolerance is smaller than 1 millimeter. So in OPT3, you can see everywhere when we compare the edge of our blank with the target line, everywhere is smaller than 1 millimeter. Okay, the maximum deviation is about 0.3 millimeter. So the software will stop. Now let me exit this history mode. What if I want to check the result for certain iterations? Maybe I want to check it for OPT3 because normally when the blank shape changed, there could be a change on the simulation result. And then I can go here, go to the OPT3, and then go to my result. And quickly check the result. Okay, so this is the post process of this iteration. It will be the same as the regular post process. So I will not spend too much time on this. You can check the FLD, sealing, string, all the post process items in the software. Okay, I think that's the first example. And next, I will show I will show you the second case here. Let me switch from here to this one. So in this case, the difference between the two cases is that this is about the trim line, not the blank outline. Also, you know, we have three operations: OP10, OP20, and 30. So let me turn on the OP10 only. So the first operation is a simple forming. We only form this stage. And then the OP20 is a trimming stage. So we will be using this trim line showing on the screen to trim the blank. And then for OP30, we will do a restrike to flange, you know, the vertical wall on this part. So also, you know, defining this trim line development is very, very simple and you know, easy. Just to pick up the trim line from the trimming stage from OP20 and also pick up the target line from our database. That's it. And now I have completed this run. So let's you know, take a quick look of the result by going to the history. Let me turn off the OPT2. I'm going to turn on the baseline run. So this is the baseline run. As you can see, we use the initial trim line to trim this part, and then there's a huge difference between the edge and our target line. So then the software will do the calculation, come with a new trim line, and apply this to the trimming stage. So it will rerun this. They're all automatic done. You don't need to, you know, interfere between this stage or between iterations. And then after it modified again in the optimization number 2, it got converged. The final difference between edge and our target line is 0.56, is smaller than 1 millimeter. We consider that as a converge. Okay, so I think that's, you know, two of my examples. I will just make a quick summary. So this is the case 1. We optimize the outline and the holes. As you can see on my screen, the initial outline we use is this green line here on the screen. Also, here is the baseline run. You can see the difference between our blank and the target line. So after we run the optimization, we do get this red line as our optimized blank outline. So now the result it's a lot better and the perfect fit with our target line. For the next case, we start with one forming, and then the trimming stage, and then the flanging. Yeah, similarly, we just you know, using this initial line, you see a big difference, and also you can see the comparison between the initial trim line and the developed trim line here. So finally, the result is also, you know, perfectly fit with our target line. We got a good result in a very, very short time. Okay. If you have any question, please type them in the QA box.
I got a question, Ming.
Yes.
I see in your first example, all right, there we have the pilot holes, all right, yes. We have the pilot pin. Now, if we are going to add some guide or pins to locate the blanks, would that pin be automatically positioned if the blank is being optimized?
Oh yes. Actually, in the old version, this does not support, you know, the update of the guide pin. But in the new version, after you pick up the point on the blank, means that you pick up the location of your guide pin. After the software modify the trim line or blank outline, that guide pin will also be updated based on the new position. It will be done automatically.
Okay, it's good to know.
Yeah,
we have another question. Yeah,
I see a
Go ahead.
question from Paul. Can the blank mesh adapt in the optimization if we have refined a long edge in the FS setup. Yes, we can, the adaptive meshes do support, in the optimization. Yeah, it's very simple answer. Okay, do you see any other question, CC?
I have another question here, Ming. Usually, what is the number of iterations that's required in blank and trimline developments, from the experience? How many iterations?
Normally it will get converged within I would say 3-4 iterations. If it's more than that, we need to check the model, make sure it is correct. But for most of the case, it will easily get converged or get good result within 3 iterations, I would say.
Oh, okay. Thank you.
Yeah.
Now there's another question. Maybe
I see another question
answer,
from Wayne. Is output of blank giving in line segment or line arc spine? Actually, the output will be line. It will be a IGES. Actually, after the software modified the line, it will output an IGES file in the folder, and also that line will be imported into the database. So after the optimization, you can find that line in the curve manager in the post, or you can use it in in the. Also, you can find the IGES file in the folder. You can use that line to modify your blank, or just directly use that line. Is it clean? Actually, it's still at the level of the Dynaform. It's not curvature smoothed, so it means that you will see some control point there. But you can easily smooth the line in the CAD software, I believe. I hope that answer your question.
We are using a B-spline in Dynaform, right? So we don't. It's not breaking down into art, but it's a spline.
All right. Do you see any more questions, CC? I don't see it.
Yeah, we have a question regarding the target line inside, middle, or outside. JT already answered that, but maybe you can kind of bring it up. Mink, is the target line inside, middle, or outside of the material?
Oh, actually, it's in the middle of the material.
Okay. In the middle of the material. All right.
Yes.
Great.
Yes, we have answered that.
What is the lowest range of accuracy? Like millimeter. So
Yeah, normally we'll use 1 millimeter, or even use a smaller. You will the software will find it's difficult to get converged. It will run more iterations, but you will see the deviation is still in a high range and never may fall into that tolerance. So it will just keep running. So maybe we need to check the model, check the refinement of the mesh, and also make sure this. I would say use a larger value will help get converged. Okay. If there's no more question, I will just wrap up.
Yeah, I think we should, and I think the recording will be sharing with all the participants, right?
Yep.
Okay, so we can wrap up this. If there's no more questions, Ming.
Yeah, thank you everyone again for attending to this webinar. And like CC mentioned, please subscribe to our YouTube channel. And for the previous webinar, for the technical video, and also the record of this webinar also. And also check the information for our next coming webinar. Please go to our new ETA website, eta.com. You can see the information for our next webinar, blog, and ETA news. Please visit us and follow us. Thank you, everyone. I appreciate it. Stay safe and healthy, and have a great day.
Okay, thank you.
Thank you.
Bye-bye.
Bye-bye.